我先讲，然后就开始。Okay. Um, and thank you, everyone. And we will start this session. Good morning, everyone, and welcome to the multimodal dialogue system intent recognition challenge. And this competition is joint organized by the Web Conference 2025 and Taobao and Tmall group, aim to tackle real-world issues in e-commerce custom service, and more than 1,600 teams took part in this challenge. And today's session will be divided into three main parts. And first, we will have a short introduction from the technical leader of the custom department of the Taobao and Tmall. And after that, for finalists, will present their solutions. All those papers have been accepted for publication. Finally, we will wrap things up in a simple award summary. Thank you for being here today. And we will start the first part. Okay, let's welcome the head of technology of custom operation department for Taobao. Okay. 是不是？过来，差不多。
Okay. Distinguished guests and esteemed researchers and colleagues. Good morning. I'm Gang Huang from Taobao and Tmall's customer operation department. I'm the head of the tech department, tech team. Okay, it's an absolute privilege to stand before you at the ACM Web Conference, a gathering that celebrates the forefront of innovation shaping our digital future. Today, we recognize groundbreaking work at the intersection of web technology and artificial intelligence. Work that is transforming industries and redefining human-machine interaction. Okay. Let me have a brief introduction to Taobao and Tmall Group. Taobao and Tmall Group is a global leader in e-commerce, operating two powerhouse platforms. Taobao is a vibrant marketplace connecting millions of individuals and small businesses. And Tmall is a premium destination for brands to engage with discerning consumers. Together, they serve hundreds of millions of users worldwide, including tens of millions of high-value AA VIP members. At the core of this mission is the Customer Operations Department, a team dedicated to redefining user experience. Through relentless innovation, we optimize every touchpoint from browsing to post-sales support, ensuring efficiency, convenience, and delight for consumers and merchants alike. One area where Taobao and Tmall pioneered transformative change is consumer service. Here, large language models are not just tools, they are game changer. For merchants' customer service bots, this AI-powered assistance empowers sellers to reduce operational costs while boosting conversion rates. Imagine a small business owner handling hundreds of daily queries, now automated with precision, allowing them to focus on growth. Platform customer service bots for consumers, especially in post-sales scenarios. These bots resolve issues swiftly, whether tracking a delayed package or processing a return. Speed and accuracy here translate directly to trust and loyalty. Central to both is user intent recognition, a critical model that deciphers consumers' needs from text, images, and even multi-turn dialogues. To tackle this complex problem, Taiwan Tmall Group partnered with ACM to launch a global competition. The challenge is to advance multimodal intent recognition in e-commerce. 1,600 teams from around the world participated, navigating two pivotal tasks. Task 1 is image scene classification. Task 2 is multi-turn dialogue intent recognition classification. After rigorous preliminary, nine teams rose to the top. Today, we are going to welcome 4 finalist teams here in Sydney to present their visionary solutions. Let's turn the spotlight on these finalists. Final solution 1, boosting e-commerce user intent recognition with self-data augmentation and structure-aware retrieval. Final solution 2, towards intelligent multimodal intent recognition in e-commerce dialogue system. Final solution 3, multimodal intent recognition in customer service via data augment and LLM merge. Final solution 4, optimized discriminative vision language models for efficient multimodal intent recognition. As we prepare to honor these finalists, congratulations to all participants and a warm round of applause for our finalists. Thank you and enjoy the rest of the conference. Thank you.
Let's start the first solution, the IntentionGPT teams. Okay. 你要演讲者模式吗？等一下啊。PPT 打开了吧？打开了是吗？对。OK， 你是直接播放模式还是演讲者模式？你是演讲模式还是直接播放？我直接播放了。那就直接放这个。OK， 那就是。
Hello everyone. Good morning. My name is Yilun Jing and from the Southeast University, Nanjing, China. Today, I am honored to present our work titled IntentionGPT Boosting E-commerce User Intent Recognition with Self-Data Augmentation and Structure-Aware Retrieval. This work has conducted with my... What? The screen haven't been shared. In Zoom and share screen. Yeah. Oh, okay. Share. Okay. And this work was conducted in collaboration with my co-author, such as Wu Chunqi, Pan Xuming, and so on, and affiliated with Southeast University and Hangzhou Yugu Technical.
Okay, sorry.
Okay. Hangzhou Yugu Technologies. Today's presentation will be focused on our paper and we who position.
First screen is full screen.
全屏 OK 了吗？
这有一个这个档。
这个 OK，
啊，我不知道这个，在这儿，它那个界面板在哪？OK，
We hope that our IntentionGPT can provide an effective solution to challenges of data scarcity and domain adoption in e-commerce user intent recognition. Here is outline of today's presentation. We will start by discussing the background and motivations, then elaborate our proposed intention GPT. And finally, we will present our experiment results. First, let us look at the background of our research. In the e-commerce domain, multimodal user intent recognition is crucial. It is essential for tasks like personalized recommendation, market personalization, and optimizing shopping experience. Accurately to identify user needs across multiple dialogues can allows e-commerce platform to better match products and service to customer expectations, thereby improving satisfaction and conversion rates. Traditional intent recognition methods such as sport vector machine, decision trees, or frightened pre-trained models like BERT perform well with large amounts of high-quality labeled data. However, these methods heavily rely on costly and time-consuming manually labeled training data, making their real-world implementation at scale difficult. So in recent years, the large language model have shown significant advancements in multimodal task and offering new potential solutions. Yet, this model typically train on open domain datasets struggle with understanding the fine-grained semantics specific to the e-commerce domain. So let's further elaborate on our motivation. Although this model trained on large-scale general open source datasets, this means they lack the ability to be aware of the fine-grained semantic within e-commerce domain. Query in e-commerce often contain specific technical terms, concepts, or implied intentions. For instance, when a user asks, "Is this 7 a general large language model might only understand it as a white unit inquiry, but the user's actual intent is asking about product usage. This gap between general understanding and the actual intent in the e-commerce domain is a key challenge for a large language model in this context. So let's summarize the main problems and the technical challenges we face. E-commerce domain lacks large scale, high quality, labeled multimodal user intent data. And our research focuses on a senior with limited labeled data, specifically fewer than 50 annotated samples per intent class. Existing general large language models struggle to effectively capture these specific fine-grained semantics and contextual information in the e-commerce of domain-specific knowledge. Therefore, our core problem is how to enhance of the ability of the large language model to accurately to recognition fine-grained user intent in the e-commerce platform, especially under the condition of the limited data. To address these challenges, we propose the IntentionGPT, which with enhanced intention recognition abilities with a new self-data augmentation method, a new collaborative consistent filter method, and the new struct-aware retrieval method. And finally, we apply model fusion to further enhance the ability of our model. First, the first core component is the self-data augmentation method. To tackle the data-limited challenges, we leverage a small number of seed-labeled samples to generate a large volume of diverse synthetic samples. We simulate realistic e-commerce dialogue scenario by creating user agents and customer service agents. User agents generate questions based on the predefined personalities, purchase motivations, and product image. While customer service agents respond according to product information and business rules. This simulation naturally incorporates multimodal elements and multi-turn dialogue flows. Through this method, we can generate 10,000 high-quality synthetic training samples from just 1,000 seed examples, significantly expanding the training data. The second component is collaborative consistent filtering, or also named the CCF, to mitigate the potentially noisy introduced by self-data augmentation and further enhance data qualities. We first use an version language model to auto-label the synthetic data. Then we encode both text and image into embedding vectors and class sample through k-means. We compare then finally we compare the vision language models labeled results with the class assessment. If a samples in the vision language model label disagree with is a cluster label, we consider it potential noisy and filter it out. This collaborative filter mechanism not only combines semantic analysis and vision language model verification to help construct a cleaner and high quality training data set. The third key innovation is struct-aware retrieval. To further enhance language models' multimodal reasoning ability and introduce more domain-specific knowledges, we apply a retrieval augmented generation method. While this RAG has potential generic, retrieval can introduce more noisy. So we propose a struct-aware retrieval method. First, we construct an attribute-aware graph, treating text and image as nodes. Then we build a similarity index based on the cosine similarity and the inherent integers based on the dialogue relationships. Then we utilize the graph attention network to flatten the graph struct. Graph attention network can effectively captures complex node iterations and learns better representation that incorporates structured information. And during the inference stages, we use the graph attention network to enhance the representation for retrieval, fetching domain relevant knowledge samples related to the query. This structure-aware approach helps improve retrieval accuracy and robustness, especially in data-limited scenario. The fourth component is model fusion. To further improve model performance and robustness, we employ the model soap method. Fusing the weights from the model chain on the different stage. Our observation is that early stage models tend to generalize well and capture generalized patterns, while later stage models are better at learn fine-grained features. By fusing model at the different stage, we can combine their strengths, balance generalization, and specifically to build a more robust and comprehensive intent recognition model. Finally, I will introduce experimental results. We conduct the ablation study and compare our model with the state of the art model with the SOTA model. It can be seen from the table and the figures. Our model performs best than other comparative methods. Moreover, in our ablation study, we find by removing different components of IntentionGPT, we observe the performance change. Without SDA models, we can see removing this method leads to a significant drop in the FE score. Clear highlight is their importance in generating diverse data and enhancing the model's generative capabilities. While removing model fusion also results in performance loss, validating its role in improving robustness by combining the strengths of different training stage. The ablation study and the comparative experiments strongly confirm that each core point of IntentionGPT makes a substantial contribution to improve the user intent recognition performance. And finally, to conduct our work, this paper addressed the challenge of multimodal user intent recognition in e-commerce user data scarcity. We proposed the IntentionGPT framework, which consists of the three key innovations: self-data augmentation, collaborative consistence filtering, and the structure-aware retrieval. Our work achieved first place in the SunW 2025 challenge and demonstrated state-of-the-art results in low data e-commerce intent recognition, and provide an effective solution for data-limited scenarios e-commerce intent recognition, offering practical value for creating more intelligent and user-centered shopping experience. Thank you. This is my presentation. 可以。没有喝酒。
Does anyone have questions? If no, can I kindly ask a question?
Okay, sure.
I want to ask about the evaluation metric in this page. The evaluation metric in this page.
哪个是 evaluation pages?
No, I mean how you evaluate
How
your result. Yeah.
We use data sets offered by the top groups to evaluate our method, and the data set includes the image text pair, multi-dialogues, and the label of data is the intention of the user customers, and we fine-tuned our method with the training data, including 1,000 training samples, and compare with anomaly GPT. This method is published in the 2024 AAA conference, and we compared our method with this method in the same experiment setting, and the result is here. It can be seen that our method is should perform better than them. Thank you.
And then is the second solution from Zhejiang University. Okay.
EcomMIR。
Ecom 这个吧。
是。
介绍一下叫 embarrassing
Hello everyone. It's a great honor to stand here and present our solution, EcomMIR, developed by the Embarrass LLM team for the WWW 2025 Multimodal Dialogue System Intent Recognition Challenge. This presentation will be divided into the following 4 parts: team introduction, overall of the solution, detailed method, and the technical innovations, which will cover our key innovations, explorative attempts, and some future outlooks. First, let me introduce our team. We are a group of 3 master students from the class of 2026 at Zhejiang University, and our research interests mainly focus on large language models and multimodal learning, which align closely with the theme of this competition. Next is our solution overview. The entire challenge can be understood as consisting of 2 subtasks. One is image-based sense understanding, and the other is intent classification in user's voice agent dialogues. The sense classification task involves image data paired with corresponding labels, while the intent classification task is primarily based on dialogue data. That is text with images playing a supplementary role. Our approach is to treat these 2 subtasks separately. Our approach is to treat these 2 subtasks separately, focusing mainly on the data level and model level. From the data perspective, we applied different processing strategies tailored to the nature of each data type and the specific characteristics of the two tasks. For image data, we primarily use the confidence-based data flattening and multi-source image data augmentation. For the dialoguing data in intent classification, we apply the multi-level denoising, data cleaning, data flattening, and data augmentation techniques. On the model level, we used the CLIP model for the image sense classification task and leveraged multimodal large language models for the intent classification task, ultimately generating category labels as output. Our approach mainly consists of two strategies: CN clip-based image sense classification strategy and mini CPM-based dialoguing intent classification strategy. The image sense classification focuses on two key challenges: the scarcity of training data and the difficulty of text-image alignment, which often results in low prediction accuracy. For the intent classification strategy, we mainly address the issue of noise training data by proposing effective denoising algorithms, along with fine-tuning and optimization strategies for the models. Here is our solution for the image sense classification task. We adopted CN clip, which uses VIT as the image encoder and Robota as the text encoder. The main challenge in the task is the limited amount of training data. To address this, we applied a trivial argument for data augmentation compared to random argument. Trivial argument randomly selects one augmentation type and stress, effectively enhancing data diversity. Since it doesn't require any hyperparameters, it eliminates the need for the parameter tuning and avoids performance fluctuations caused by the different settings, making it relatively stable. However, simple data augmentation alone was not sufficient, and the results will still suboptimal. To address the issue of long training accuracy, we adopted the model soup strategy, specifically the greedy soup variant. As we know, model weights are typically saved as the end of each epoch, but the best performing checkpoint might not be the final one. It could occur somewhere in the middle. Therefore, we considered multiple checkpoints and combined them. Concurrently, we first sorted the top K checkpoints based on their performance on the validation set, then starting from the best one. We sequentially evaluate each checkpoint. Checkpoint was only included in the final soup if its addition improved and the overall performance. As shown by our results, the model soup strategy significantly improved performance both in local validations and online evaluation. Here is our solution for dialoguing intent classification. The first major challenge we encountered with the intent data was the high level of noise. There was a little of irrelevant and redundant information. To address this, we proposed a multi-level denoising and data cleaning algorithm. Specifically tailored for intent data. Since the original dataset consists of multi-turn dialogues, we approached the denoising at three levels: dialoguing level, sentence level, and word level. At the dialoguing level, we observed many duplicate conversations. In such cases, we return only the first occurrences to avoid redundancy. At the sentence level, since many dialogues come from automated customer service bot, they often contain the low information phrase such as greetings, advertisements, or generic response. These were identified and replaced with empty values. At the word level, we removed please experience and thank you phrase, which contribution little to intent recognition. In addition to denosing, we applied several data cleaning operations, such as replacing long numeric strings, removing URLs, and collapsing multiple space into one. We provided a compression example. On the left is the original dialogue, and on the right is the denosed version. As shown, our denosing algorithm is highly effective and precise, returning only the key useful information. After denosing, we also merged the consecutive utterances to streamline the input further. Another major challenges we faced was the limited amount of training data. The original intent recognition dataset contained only around 300 labeled samples. So we explored ways to increase the data quality while maintaining quality. First, we made use of unlabeled data by leveraging multimodal language models. We evaluated whether prediction on the round one data were likely to be correct. We then flattered high confidence samples and added them to the training set. Secondly, we performed image data augmentation for the incommons visuals associated with the dialogues. Techniques such as rotation, scaling, and noise addition were applied to diversify the visual inputs. In addition, we noticed that the original label space was too fine-grained, which made it difficult for the large models to learn effectively. To address this, we designed a hierarchical labeling structure to better guide model training. For example, we treated single product recommendation and outfit recommendation as the categories under a border class like purchase and recommendation inquiries. With the structure, the original label single product recommendation would be abstracted to the higher levels category purchase and recommendation inquiries, single product recommendation. For intent recognition, we use the mini CPM V2.6 as our backbone model. This choice was made after extensive comparisons with several other base models, and mini CPM consistently outperformed the rest in terms of capability. Combined with other strategies, multi-level data denosing, hierarchical label construction, high confidence data filtering, and e-commerce image augmentation, mini CPM delivered outstanding performance. As a result, we achieved top one intent score on the semifinal leaderboard. The fourth point is our technical innovations. When discussing the innovation in our solution, we can still break them down into data side and model side contributions. On the data side, the main issues we faced were low data quality, limited quantity, and significant noise. For each of these challenges, we proposed targeted solutions. For low data quality, we flatted high quality data and leveraged high confidence unlabeled data. For limited data quantity, we applied image augmentation and back translation to generate additional data. And for data noise, we developed a hierarchical intent data denoising algorithm. On the model side, we address the training difficulties by separate training the two tasks. Elevated performance issues through a multi-fusion strategy, selected the most suitable base model, and improved accuracy by introducing a hierarchical intent label structure. We actually tried many different approach. For example, our first instinct when we saw the data was to train everything together using multimodal large language models, inputting all the data at once. However, the results were not good. The likely reason is that there are still significant differences between the tasks. The data distribution are imbalanced, and the data volumes is too small. We also tried prompt rewriting, which showed some slight improvement, but the differences was still not substantial and was constrained by the model's inherent uh, representation capability. When we looked at the image data, we consider using OCR, followed by denoising the data and calculating TF-IDF. However, the results were still not satisfactory, likely due to the noise in the data. In addition, we also experimented with removing customer service information entirely, using strategy-based image classification, image similarity calculations, and other methods. But none of these approaches yield significant improvements. Let me give an example of image similarity calculation to show how we aim to flatter high quality data. We used an image encoder to map the image data into a high dimensional feature space with the relationships between the training set and the unlabeled data serving as label 1, and the result of the fusion of both image and text information as label 2. If these two labels showed consistency, we would consider that data's label to be of high quality. However, as seen in the lower right corner of the finger, the data points for each category was scattered and didn't provide a clear distinction of which label belonged to which image, making this approach not very effective. In fact, we tried many fancy and similarly reasonable strategies in Pertext, such as chain of thought and few shot learning, but they didn't always work as expected. This could be due to insufficient research in this area. A multimodal large model already has very strong representation capabilities, but we believe the most critical factor in this task is still high quality data. For us, data cleaning and data denoising remain key, and while this approach may be simple, it's still efficient. Finally, looking towards the future, there are a few ways we can further improve this approach. One significant limitation of the current challenge is the constraint of model with 10 billion parameters. To address this, we have two key ideas. The first is to update and iterate on the base model by adopting more advanced models. Currently, we are using mini CPM, but as more powerful multimodal models emerge, we can replace it with those. For instance, we use CN clip for sense classification, and if a better image and text encoder with better Chinese adaptability becomes available, we could switch to that. The second idea is to explore model distillation. Where knowledge from our large models is distilled into a smaller, more efficient model. Another challenge we face is the vertical focus on the task. It's very specific to the e-commerce domain. If we had access to a large realm of e-commerce specific data, we could train a dedicated vertical large model, which would likely improve the performance of this task. Initially, we attempted to find a base model tailored for the e-commerce domain, but we couldn't find one. Later, we tried to leverage open source data sets, such as GDDC dataset, but the data quality was too low and the distribution was inconsistent. So we ultimately abandoned that approach. There are papers we referenced. Thanks for listening. That's all my presentation.
Anyone have some questions? Okay, may I ask a questions? In the feature outlook, that slide, feature outlook. Yeah. Okay, next. Yeah. So I have a question. Because in order to keep the challenge fair, we limited the model size, right? So and after our final competition, many advanced model like especially reasoning model like DeepSeek I1, QWQ of Queens, and is invited. So if we use these more powerful models like DeepSeek I1 or QWQ, do you think it's help to improve the result of our challenge?
I think the better base model can improve the results clearly. Sorry, I'm reporting here on behalf of the original authors. If you have any questions, you can contact the author with email 22351221@zgu.edu.com. Further, thanks.
Okay, thanks for your answer.
Okay. Thank you. Okay. Thank you. And so we have a break and for about 30 minutes, and we will start at about 11 o'clock, right? And thank you. So let's have a break and a coffee break.
005 and 005 in Zhang and I were mainly responsible for model fair tuning and model merge, where our teammates from UCAS focus on image augmentation. Our solution is divided into three main parts. we oh sorry，这个正好打住了。没关系，这样去的话，这鼠标没有，它有，但是它是个演示的模式，所以它是，哎，先退出一下，没有，然后把这个缩小这个，来，往它这个下，对，可以，好，这小区吧，先。Okay. Let's go on. Our solution is divided into three main parts. Three main parts that various data augmentation technologies to the training image, including different image transformations. Then we perform for parameter fine tuning on the base model using the augmented data. Our base model is Queen2 via 7 billion instruct. Finally, we merge the different fine tuning models into a single model to enhance the performance. Model merge is a relatively new technology that have attention in the past year or two. It mainly involves the processing and merging multiple models at the parameter level. The simplest example of model merge is the weighted sum of multiple models. At the beginning of the second round, we at the beginning of the second round, we submitted the results using our best performing model from the first round, but with different image resolution parameters during inference. The model had original being fine-tuned with images resized to 800 pixels. Our results showed that the image resolution had a significant impact on model performance, especially for scene recognition, which is far more sensitive to resolution than intent recognition. Therefore, we experimented with merged models fine-tuned at different resolutions. For example, although we used the same model 35 as the base, we have two models were fine-tuned with slightly different data augmentations. Transformer 6 is used 800 pixels, while Transformer 5 used 512 pixels. Since model 35 was trained at 800 pixels, so the 512 trained model competed model 35 shortcoming in handling multiple scales. For scene recognition, more diverse image augmentations help the model learn a richer set of features, improving the generalization. Model 36 and 38 had different strengths. One formed well in scene recognition, and the other is intent recognition. So we merged them into model 40. Model 40 retained model 36 strong performance in scene recognition and also showed improvement in intent recognition. This demonstrates that model merge can combine the strengths of the different models and even lead to performance imagery in a specific task. We then expanded our training data by pseudo labeling 100,000 text1 samples using the model from the first round. However, while the pseudo labeled data helped enrich the model parameters with high accuracy and diversity in intent recognition, model 36 had a high, model 36 had a high error rate when labeling 5,000 scene recognition samples. This resulted in poor performance during training and ultimately weakened the merged model's scene recognition ability. Considering data accuracy and diversity, we decided to use only 1,000 high-quality training samples and select 500 scene recognition samples from the text one in the first round, discarding large portions of the noisy pseudo-labeled scene recognition data. This way, we increase the scene recognition data diversity while ensuring high data accuracy. Given our time and submission constraints, this combine was a practical trade-off. If you have chance, you can try more choice. By filtering on a data set composed of 1,000 training samples and 500 selected text one samples, we adjusted merged parameters. We found that overfitting intent recognition data negatively impact on original models' competitiveness. Effective training requires balance both data quantities and data qualities. Model merge have parameters such as density and weight crucial. The density parameters controls the percentage of weight difference retained during merging. While weight determines the relative contribution of each model to the merged result. Finally, we applied 8 random transformations to the 1,500 samples to further increase data diversity without compromising accuracy. After training and merging with adjusted parameters, the results shows that altering the image information helps the model learn from multiple perspectives, enhance generalization. This gain confirms the significant impact of merge parameter tuning on the final model performance. In the final summary, I will say there are 2 key points in this condition. The first one is the data augmentation. There have 2 aspects. The one is the balance between the data size and the data accuracy. We need we don't only focus on data size, but we not only focus on data size, but also we need also focus the data accuracy. So the other aspect of the data augmentation is the image enhancement, because the image has many information, have more information than the text. The second key point is the model merge. For the model merge, our experiments tell us that first we should train different child models, and secondly we need to tune different merge parameters to have best performance. Okay, thank you for your time and attention. That's all. Thank you.
Thanks for the brilliant talk. And does anyone has any questions? If no, can I ask a quick question? Can you turn back to the page 14?
14?
Yeah. Yeah. Sorry, maybe one page 13. Yeah. Can you introduce more about the detailed augmentation methods?
Which one?
Can you introduce more about the augmentation methods? It seems in the
it's just some default functions in the Python transform this import the transform. There have some just it's all they are all some default functions. It's simple. For example, we resize the picture, or we have some mosaic in the picture, or we have
So
large
the classic ones, right?
yes. So
Okay.
it's very simple. So but and it's useful.
Have you conducted evaluation study according to the augmentation methods?
No, sorry.
Have you conducted ablation study with respect to the augmentation methods?
We don't have we don't spend time on
But empirically, you find that they are very effective, right?
yes.
Okay, thanks for your answer.
And solution is from okay.行业方法对吧？这个对吧？Okay. So seeing the last team is not in Sydney, so he will present by him. Okay. Yes.
I will show the team advantages work in there because they have some reasons. So unfortunately they can't attend the conference today. Okay. Ladies and gentlemen, greeting to you all. We are the Advantage team from Zhengzhou University. Next, our team will be sharing the proposal and the paper for the WW 2025 Multimodal Dialogue System Internet Recognition Challenge. Our evaluation paper is titled Optimizing Discriminative Vision Language Model for Effective Multimodal Intent Recognition. The team members are Jin Wang Song, Zhang Tianhua, Hong Ying Zan, Ying Jiehua, and Ming Peng. First, I will briefly review the competition task. The objective of the competition is to effectively recognize the customer intentions in e-commerce customer service conversation. It comprises two main tasks: image scene classification and dialogue intent classification, and is divided into two stages: the first round and the second round. There are also several strict restrictions for this competition. Now let me introduce our overall solution. This is an overview of our approach. We optimize the model's performance from three aspects: data, training, and enforce. In terms of data, the last model part of the figure, we use the image and text augmentation to enhance the training data set. During the final round, we also applied semi-supervised learning, especially pseudo labeling. Regarding training, in the first round, we conducted instruction tuning on the inter-VL 2.5 8 billion model. In the final context stage, we performed discriminative 4-parameter tuning on the Queen2 VL 7 billion instruct model and optimize the classification and initialization to improve fine tuning. For inference, we use the TTA to generate diverse model outputs and integrated them. Next, I will elaborate on each component, beginning with the data augmentation. For image augmentation, we use image transformation to boost the quality of training image. However, we found that the picture dataset here contains crucial textual information. So cropping and rotation, which can damage text information, were avoided. Instead, we mainly adjust the brightness, configuration and construct. For text augmentation, we optimize the instruction by adding a details label name explanation. In the image scene classification task, we incorporated OCR results into the instructions to enrich the text data. When training, we mix the augmentation data with the original training set to form diverse training samples. In the final round, we divided into semi-supervised learning. As the final round allowed the use of the first round data, we first labeled the first round text data as a pseudo label. To enhance the pseudo label quality, we screened the labels by confidence. Specifically, we use the net token loss on the label part as a confidence metric. For each category, we sorted the data by loss and selected the top 50, 100, or 60, 100 with the lowest loss to join the training set. For image scene classification, we took the top 50%, and for dialogue intent classification, the top 60%. In the training process, different methods were used for the first round and the second round. In the first round, we employed the LoRa method to conduct generative instruction tuning on several VLMs. All data was transformed into the instruction output format to accelerate the convergence. We computed the loss only for the output. For example, the target labels. A validation set was random split from the training data to identify the optimal checkpoint during training. To optimize the time and memory efficient, we use the advantage technologies like 8-bit optimizers, granted checkpoints, granted accumulation, and linear kernel focus linear loss function. We developed a custom file tuning framework that allowed real-time competition of the model's FU score on the validation side during training. The table below shows the happy parameters we used during the first round. In the second round, we tested several models, including Queen2VL, InterVL 2.5, Obvious 1.6, and Valley 2. The table below shows the online results after fine-tuning these models. It should be noted that Obvious 1.6 9 billion with 10.2 billion parameters. Among the four models, Queen2VL and InterVL 2.5 performs the best and were used in our sequence experiment. In the final round, we conducted a 4-parameter discriminative file tuning on the Queen2VL 7 billion model. Specifically, we treated the task as the sequence classification problem. The input sequence will processed by the decoder layers of the VLM's language model. We use the hidden state of the last token as the sequence representation and feed into a linear classification hand to product logits. Cross entropy loss was employed as the training objective. The main reason for using discriminative file tuning in the final round is higher efficiency. In generative approach, the hidden states mapping to the vocab space through the language model hand, which consumes a lot of VRAM. Best construct in discriminative approach, logits are only mapping to the label space, which can be negligible in terms of VRM and use. With the discriminative approach, we can form 4-parameter file tuning on Queen2VL 7 billion with within 48 IntentionGVRAN. In terms of inference speed, the generative approach requires multiple forward passes. While discriminative approach only need one forward pass to obtain the final logits. This significantly improves the performance efficiently. However, discriminative approach can cause a mismatch between the pre-training and the fine-tuning stage. The classification hand is randomly initialized, which is not aligned with the model. This leads to an unstable fine-tuning process and affects the model performance. To solve this, we reuse the weights from the pre-trained language model hand to initialize the classification hand. In our experiments, the LTI method shows significant advantages over the randomly initialized classification hand. LTI coverage is faster and has lower loss and achieve better performance. The table shows the metrics of both methods over the validation set. Clearly, LTI has a higher metrics and better performance. In the inference phase, we considering the model ensemble technicals. However, competition rules state that ensemble model were counted by their total parameters. For example, 2 7 billion models would count as 14 billion, exceeding the limit. Thus, we opt for the TTA instead. In the first round, we achieved the best score of 87.69. In the final round, our score was 19.009. Okay, it's the conclusion. It's all. Thank you.
Because also it's not here, so maybe there's no question. Okay, and we come to the last session, and we will have a award ceremony, and so please and welcome the head of technology. Okay, and so the first award is from the team of Dynamic Challenge, and please come to the board too. Okay. OK， 我换成那个。对 ，OK。看一下啊，我也没有关掉，是这个吗？对，我就放第一个就 OK， 把它全屏。全屏，对。然后OK， 我来。那个。你拿着，然后我拍一个吧，你拍一个是这个。那我先看那个，我啥你。没关系，你先。哦，挺三的。OK， 要不让他自动拍，你看，这个让我去拍就可以了。好。1、2、3、4。And the second award is from the team of embracing the LM, and would please come to the front. 我还是要跟你，对，Ecom 对吧？这个没错吧？你看一下。 OK。3、2、1、3、3、2、3。OK. Congratulations. And the third award is from the team of Scale, right? OK. 然后把你这个是这张啊，是这张比较好是吧 ？OK。那就还可啊。好，Thank you. Have pleasure. Okay. And thanks for attend this meeting, and we will finish this session. And last, we take a photo, okay? And yes. 那种拍的这一照，往我多讲述他们一起来。对，你帮我拍一下，好，帮我，然后我来把这个放在第一页。你安排一下大家在那个，我们宣传就那个培育那个。
第一页宣传淘宝的呀。
这个是吗？
对，第一页吧，对呀。
这个是吧？
哎，对，那肯定是这个。
OK，就这个。大家一起上来拍个照吧，谢谢。他们是可以生发很光彩，三个人站，后面看不清，后面就是对，那咱站。是，就是这样。那个说的后面不对。或者说想，你觉得让我站？哇，北京今天对。是不是说我也非常是不是？但是啊，但是哦，哦，对，没有，好像对。Thank you. 我把这个就关了啊。OK。